misfire. Yeah, that right there is telling you it's a mechanical problem. Okay, so keep that in mind. So here's a quick video of what a bad cylinder sounds like. Okay, and I actually borrowed this from Paul Danner, Scanner Danner. I don't own the rights to this video. Hopefully he doesn't mind that I put this on here. I borrowed this from him. This was a great capture, and just listen to it. Okay, so you hear how the engine's not consistent. It's ta 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 instead of ta 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 ta. Okay, that's what you're actually looking for. All right, I accidentally put this slide in there twice. I apologize for that. All right, so let's do some quick examples. Okay, engine compression. We do a static compression test. So when we're talking about engine compression or static compression, that's all spark plugs removed, throttle plate wide open, okay? And you're going to crank the engine the same amount of revolutions for all cylinders, and then you are going to document it. So right here I'm giving you guys an example. Cylinder 1 is 160, 2 is 155, 3 is 130, and cylinder 4 is 160. Now, do you guys see any problem with one cylinder that might be low? If you guys answered 3 followed by 2, you guys are on point, okay? Cylinder 2 is 5 psi below. However, we usually use a rule of thumb of 10%. They need to be 10% of one another, and number 2 is within 10%. It is a little bit low, but it is within 10%. The culprit here would be cylinder number 3. It's low on compression during a static compression test. So after we do that, then we're going to do a running compression. With a running compression test, we want to see that the engine's running at higher RPM. So we're going to have a lower compression. That's absolutely normal. What you do want to see is you want to see about a 50% drop in compression. Okay, so cylinder number 1 is at 180, cylinder 2 is 78, cylinder 3 is 65, and cylinder 4 is 80. Just to go back here, number 1 is 60, 55, 130, and 60. 60, that's fine. That was a little bit high. 130, 65, that would be on point. And cylinder number 4, that would be on point as well. So it looks like cylinder 2 is actually the one that's a little bit on the high side, but not too crazy. Okay. All right, and engine compression. So once we do a static compression test and we see a cylinder that's low, we're going to run a running compression on that particular cylinder. If it's not below the 50, then we're probably going to have an exhaust issue, and then we're going to go from there. We do a cylinder leak down test and whatnot. One of the other tests that you can do is you can do a snap compression test. So on that same cylinder that gave you a low static, do a running and then follow that up with the snap test. Snap test needs to give you between 75 to 80% of cranking compression, and it's telling you how well the cylinder can inhale and actually exhale. Okay, so looking at it here, which one is actually giving you guys a problem? And if you guys say cylinder number 2, you're spot on. Okay, cylinder number 2 is 77 psi, which is not 80%. That's giving you guys letting you guys know that we have a problem. Based on it being a lower reading, that's usually indicative of a breathing problem. So the cylinder can't inhale properly. So that's probably an intake restriction, carbon buildup, misadjusted valve, or a bad intake valve. Okay, so that's something that if you can put those pieces together, you can come up with a diagnostic plan, execute it, and then repair a vehicle successfully. Okay.
Trade executed.
If your compression tests all point to a bad mechanical issue, then you're going to follow that up with a pinpoint test. This pinpoint test is a leak down test. What you guys are seeing here is we have a leak down tester connected to the cylinder. You're going to raise the cylinder to top dead center compression, both intake and exhaust valves closed, and then you're going to introduce shop air. I put a good scale on here for you guys. If the reading's good, it's usually between 0 and 10%. Fair would be 10 to 20%. Poor is 20 to 30.
Trade executed.
And it failed if it's anything above 30%. For a cylinder that's more than 20%, pinpoint the cause. It could be air escaping through the intake valve, exhaust valve, or PCV system. So whenever you guys are doing a leak down test, okay, there's going to be shop air being introduced into the cylinder. It has to go somewhere. So if you're getting more than a 20% loss, at this point now you need to figure out where is this air going. First thing you're going to do is you're going to remove the boot for the air intake and see if you can hear air coming out of the throttle plate. And if you do, it's a bad intake valve. Okay. Next one would be pull the dipstick or remove the oil cap. If you have a bunch of air coming through there, that means you got bad piston rings. Okay. Then the last one, we take a glove and shove it over the exhaust, and if that glove begins to inflate, we know we got an exhaust valve that's not sealing properly, and now we can pull the valve cover off if we still have diagnostic time. If not, at this point, we can ask the customer for a teardown, and then we can pinpoint and tell them exactly why that problem is occurring. One that I forgot to mention was bubbles in the coolant. You're also going to take the radiator cap off, and if you have bubbles in the coolant, that means you have a blown head gasket or a cracked block. Okay. One thing that I learned not too long ago from PJ Walter was test it bottom dead center. Okay. I didn't really touch on this, and the reason why is because this is going to be counterintuitive to anything we teach you in any class. Plus, it's not going to fit with ASC testing. But one way that you guys can actually test for a cylinder, a bore that might be damaged, is put the cylinder on bottom dead center with both valves closed and then do a leak down test. Because now if you're getting bubbles, then there's a high probability that it might actually be the cylinder walls, not the actual cylinder head. Okay, just a word of advice there. All right. This next part that I'm going to be talking about is 5-gas analysis or emission diagnosing. And to me, this is actually a great tool to use, even though a lot of technicians say, oh, no, it's old technology, you shouldn't be doing that. It works, and I love using a 5-gas analyzer anytime I possibly can. I love teaching it because it makes diagnosing that much more easy, especially when you guys are a drivability tech that all you do is fix cars that aren't running properly that nobody else can fix. 5-gas analyzer is going to be your best friend. So analyzing air and fuel, air is made up of nitrogen and oxygen, and fuel is made up of hydrogen and carbon. Those two get drawn into the cylinder, they get compressed, and then they get ignited. Once they get ignited, then we're going to have some exhaust gases that are going to be changing as elements. So we're going to have H2O, we're going to have water coming out of the exhaust. So the small droplets you guys see is absolutely normal. The old rule of thumb is for every 1 liter of fuel, you're going to get 1 liter of water. Okay, so for every 1 hour of fuel burned is how much water you're supposed to see in the exhaust. Now, if the engine's not running properly, you're going to have some hydrocarbons left over. Typically, all the new cars I've seen now are at 0. Carbon dioxide, so that's going to be carbon and oxygen combining to form CO2. When I don't have enough oxygen to form carbon dioxide, I'm going to form carbon monoxide, the silent killer. Okay? And usually when I don't have enough oxygen, that's indicative to me of I have too much fuel. Okay? So we can't produce CO2, we'll produce carbon monoxide, the one that's going to kill you. Then we have some oxygen left over. And obviously, because we breathe in nitrogen, nitrogen is a gas that responds to temperature and pressure. Nitrogen is going to combine with oxygen, either 1, 2, or 3 molecules of oxygen to form NOx. Then NOx is a byproduct of internal combustion that if it mixes with HC in sunlight, then it's going to create photochemical smog. So when we're talking about the 5-gas analyzer, CO2 is a measurement of combustion efficiency. Usually you want to see, CO2 about 13 to 15%. The higher the better. Low CO2 indicates an engine mechanical, fuel, or ignition problem. So if you think it might be a mechanical problem, put a probe in it. Put the emission analyzer probe in it, start the car, and look at CO2. If CO2 is in the 10s, 9s, you got a pretty bad problem. You got a mechanical fault, okay? Oxygen. Oxygen is also measured in percentage, and it tells us how well the catalytic converter is running efficiency-wise, okay? O2 should be about 0%, okay? And high O2 indicates a lean condition or a misfire. Hydrocarbons is measured in parts per million, okay? And HC is a measurement of raw fuel in the exhaust. So hydrocarbon should be about 50 parts per million or less. And if HC with high O2 and low CO2 would indicate an ignition misfire. High HC and equal O2 and CO2 would usually indicate a mechanical misfire. And like I said earlier, carbon monoxide is when we don't have enough oxygen to create CO2. CO2 is measured in percentage. CO is measured in percentage, and CO should measure about 0%. Low CO indicates lean. High CO indicates a rich condition. We tested a GDI vehicle the other day, and CO was 0, and we were seeing CO2 in the 16s. So it's there. Okay. NOx is measured in parts per million, and NOx is created when nitrogen heats up and expands and combines with oxygen. NOx should be about 250 ppm, and anytime temperature increases above 2500 degrees Fahrenheit inside the combustion chamber, that's going to help us increase NOx production, so then NOx goes through the roof. That's why we use EGRs, and the EGRs help us reduce that amount of NOx. All right, so here we have a quick case study. The vehicle has 15.6% CO2, 0% O2, 68% hydrocarbon, 0.11 CO, and then NOx is 141. So what I did here is I plugged them into a Lambda calculator. If you guys aren't aware what Lambda is a measurement of how well the engine is in fuel control using 5-gas analysis. This is actually a way better method of determining if the vehicle is in fuel control, better than actual long-term and short-term fuel trim. This is a European thing. It's getting traction here in the States. I actually teach it and use it quite a bit. And if you guys want to use the link, you guys could see it right here down below. So if you guys notice, our Lambda result is 0.995. So that right there is indicating to me that the vehicle is running rich, not crazily rich, but it is running a little bit on the rich side. If I look at CO, I have 0.11, so that's also verifying that it is running a little bit on the rich side. And then hydrocarbons is also re-edifying that by hydrocarbons being at 68 ppm. So that's telling me that there is some unburned fuel left over, and that's letting me know that there's too much to begin with, can't burn it all, so I have some left over. Okay, so that right there is letting me know that I might have a small misfire, okay, or a fuel delivery issue, one of the two. So the vehicle has a Milon PO300 DTC, okay, and let's take a look. CO2 is at 10%, O2 is 3.5, hydrocarbons is 320, CO is at 0.11, and then NOx is at 42. Our Lambda calculator is letting us know we have a Lambda reading of 1.205, which means this vehicle is excessively lean. It's actually far beyond the normal lean threshold of 1.020. So this is telling me this vehicle is already into a lean misfire situation. So this vehicle here is having not really a lean condition. It's just since we're not burning the air fuel mixture, this is why O2 went up, CO2 dropped, and HCs went up because it's not being consumed, so it's going right out the tailpipe the same way it went in. So this is why we're getting what's called a false lean condition. This is why it's important to understand, is this really the cause of the problem, or is this an effect of the actual problem? Okay. All right, ignition system, diag, and repair. Whoops. So misfire DTCs and HC emission failures are attributed to one of three things. It's either a mechanical problem, an ignition problem, or a fuel problem. Okay, that's about it. It can't be anything other than that. Well, it can. I don't want to say can't. It can be something other than that. However, about 98% of the time, it's one of these three things. Okay. So, engine mechanical can be determined quickly by a general test, like an RC test. After mechanical general test, if it seems normal, move on to the next area, which would be ignition. So this is what I'm referring to. Car comes in and it has a misfire. Instead of you guys going and grabbing tools, taking the intake off just to swap coils, and then if that doesn't work, then it's like, now what? Why not just run an RC test? Connect an amp clamp and positive, negative across the battery and run the test. Now, if you notice that one of your humps is smaller than the other, you know it's a mechanical problem. Don't waste your time testing everything else because it's mechanical. Does that make sense? Okay. If that general test comes out normal, then that means it's not a mechanical problem. Then move on to the next thing, which would be ignition. Okay. So with ignition, there's multiple tests you guys can actually run. If you still have a vehicle that has distributor and coil, then you can just plug onto the coil side, primary side, and then secondary off of the coil, and then watch for an event that might determine which cylinder is the one misfiring. And if you have a newer car with coil on plug or intelligent coil on plug, then you're gonna have to do a test like you guys are seeing on the screen right now. What I'm doing here is that I'm testing the primary side of the coil using a current clamp. So my current probe is actually clamped around the coil, and I'm actually checking for current saturation. Is this coil shorted on the primary side, and is it able to produce enough voltage for the secondary side? So what I can see here is that it didn't have a short, and the reason I say that is because usually if the coil is shorted, that means less resistance, so this is going to shoot automatically up and then ramp off. Because it didn't shoot up, that's telling me that it's not shorted, and this primary side should be able to create enough energy for the secondary side. Here, I'm looking at a non-intelligent coil where I took a back probe and back probe the ground side of the coil, and I'm also getting this same waveform. Okay, so this is the same thing, we're just looking at it in different parts of it. This is current or amperage, and this is voltage. Okay, so that's why we can do it either way. Again, this test that you're seeing right now on the screen, the primary side and this type of waveform, can only be done on a non-intelligent 2-wire coil. If your coil has more than 2 wires, you cannot run this test. You got to do this one. Okay, keep that in mind. So what you guys are seeing here is, here we can see that the dwell time, so this is coil saturation, and then here the coil gets turned off, energy gets built to overcome or ionize the air gap of the coil, then energy begins to shoot across the actual spark plug gap, and then some coil oscillations, and the waveform begins all over again. So here you're looking at the primary side of an ignition system. This is a superimposed pattern. This voltage trace for all cylinders are displayed one on top of each other. So if you have one that's really bad, it's going to stand out. Okay, so on the primary side, which is the low voltage side of the coil, we're looking at the firing section. That includes firing kV and burn time. This whole area right here would be the firing section. Section immediately after that, where the nose begins, coil oscillation, and then right before dwell, is known as our intermediate section. And then following that is our dwell section, the amount of time that the coil is actually on, saturating to create energy. So let's take a look here at our primary side of an ignition coil. So part A right here is turned on, coil is turned on, saturating the primary side. Part B, current limiting. So we don't want to produce too much current. So what the system's actually doing is it's turning off the transistor to the coil, so the coil stops producing energy. Then right after that at C, we actually turn it off completely. Then what do we get? We get a rush or a spike of voltage. And that's absorbed into the secondary side. So right here you're watching the primary being turned off and being absorbed to secondary. At part D is where the voltage required to begin to ionize the actual spark plug gap. Okay, so what happens is we have to create a bunch of voltage to be able to jump all the compression and that 30 thousandths gap between the electrode and the plug tip. Then it's not just it shoots across, right? It has to create enough energy to be able to begin to arc, and then once it actually starts arcing, that's when we begin to get the burn time. So part E, voltage stabilizes from 200 to a few thousand volts where plasma is created, and then spark begins to travel across the spark plug electrode. Part F is our burn time. So if you have an upward, that indicates a lean condition. So if you see it start from point E and just go straight up, that means that there's no hydrocarbons inside the combustion chamber. So it can't produce, or excuse me, it can't create what's called conductivity. Because we don't have a wire or a circuit inside the combustion chamber, we have to create that plasma, and we need that hydrocarbons for us to create conductivity. If we don't have that, then voltage is just going to shoot up because it doesn't have a path back to ground through that compressed hydrocarbon. And then if you get a downward spike, then that's a downward ramp. That means there's too much fuel, so we can't properly burn it. And usually you're going to get a downward spike, and it's going to be a lot longer. The reason why it's a lot longer is because it needs to burn longer to burn all that air-fuel mixture inside the combustion chamber. And looking at F, your burn time should be a 1.0 to 1.5 on a coil-on plug system. So if you got a vehicle that has coil-on plug, you should see 1.0 to 1.5 burn time, okay? A lot of people ask me, what about KV? It doesn't matter. Burn time. If burn time gets longer, KV gets shorter. If KV gets longer, burn time gets shorter, okay? It's just, if I have 12 inches of rope and I lift up 8 inches, that's going to only give me 2 inches left over. But if I pull it 9 inches, that's only going to give me 1 inch left over, okay? So think about it that way. If KV goes up, burn time gets shorter. If KV goes down, burn time gets longer, okay? Another thing you always want to do is split the burn time in half. If you split the burn time in half, any issues to the left-hand side, okay, is going to be indicative of a problem external of the combustion chamber. Anything on the right-hand side is indicative of a problem internal of the combustion chamber. So let's say if we're looking at this graph here and this KV is just off the chart and I have very little burn time. Where's the problem? The problem is external to the combustion chamber. So that's going to be spark plug wire, cap, rotor, coil boot, or the coil itself. Now, if I'm looking at it and I split it in half and right after about the halfway mark, I just begin to see some very violent hash. Okay, what is that telling me? I have a problem internal to the combustion chamber, which is probably going to be a valve problem. Okay, why? Because if the voltage goes up, that means if it lost fuel, and if it goes down, it found fuel. So if I start to see a big hash, that means no fuel, found fuel, no fuel, found fuel, no fuel, found fuel, no fuel, found fuel. The only way they can create that is if I get some turbulence because of a valve that's not seating properly, okay? On point G, we call it the nose. If you don't have a nose, no spark event happened in the cylinder. That means something happened where there was an event of spark, but it didn't happen in the combustion chamber. And part H is the remaining energy that's not strong enough to continue to burn, but it just begins to dissipate. You usually want to see about 2, okay, of those little hash marks or little humps. That's going to be an indication that the coil fired properly and everything went to plan, okay? So the firing line should jump abruptly at the moment the throttle is open and then return to the previous level at idle. So if you have your KV there, right, and you go and snap the throttle, then you should get an increase and then it's going to come back down to normal. Right? If you get one that when you go to snap it, you have one that takes a little bit longer, it comes up, but then it like half a second later than the rest of them to come back down, and then it does a tut valve guide or valve spring, okay? If you go and you hit the throttle and you have no KV change in that cylinder, that means that cylinder didn't change, so that means you didn't get an inrush of air, so that's why compression didn't change. So you probably got an intake timing problem or an intake valve problem on that particular cylinder. So what you want to do is you want to raise RPM to 2,500 RPM, then quickly release the throttle. If one cylinder KV drops later than the others after snapping the throttle closed, then you have a weak valve spring, okay? Just remember it that way. If you're getting a firing KV that keeps getting larger and shorter, okay, what does that mean? All right, think about it. Can your spark plug can the coil boot and the coil itself get longer and shorter? No. So if KV is going bam, 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 okay, that's telling you that you got a valve problem. You more than likely got a burnt valve. The reason why is because, remember, valves spin as they go up and down inside their guide. So if I have compression that goes up and then compression goes low and then compression goes a little bit up, but then lower, but then high, okay? That's meaning that as the valve spins, then it's leaking at some points. Okay, so that's one way that you can actually see that as well. The spark plug wire and coil boot are not getting longer or shorter, so you have a carbon valve or a burnt valve, one of the two. Now, that's a general test, so now you got to do a pinpoint test to figure out if you really have a problem there and what the problem.
All right, so after we check all the ignition system, if all that's okay, the next thing we got to look at is air fuel, right? So some vehicles are equipped with speed density and some are equipped with mass airflow. What's the difference? So a speed density system uses a MAP sensor and the manifold absolute pressure sensor, and that sensor is going to be detecting engine vacuum. Engine vacuum is a good indicator of engine load. So if I have no vacuum, that means the engine's under high load. If I have high vacuum, then that means that the engine's at low speed, right? And if I have no vacuum, that means the engine's at high speed. So this is a good way for the computer to determine, is this vehicle under load or not? This is why when the vehicle has a speed density system, it's always important to verify that the vacuum line to the sensor is actually present and not cracked or fallen off. Because at that point, what you could see is, if you see 4.5 volts or near atmospheric pressure, then that's how you know that that sensor is actually not reading manifold vacuum. And then some vehicles use a mass airflow. Mass airflow has, depending on the system, some use a hot wire, which sends a small amount of current through a small little wire. As air flows through that wire, it cools it down, so the computer is paying attention to how much current it needs to maintain a certain temperature, and that's how the computer knows how much incoming air is actually coming into the engine. So the speed density system measures intake airflow by sensing changes in the intake manifold using a pressure type sensor. For those guys that are advanced scope users, some of you guys might be using a MAP sensor with a 5 volt reference box as a delta pressure sensor, an absolute pressure sensor. So you're using it to measure vacuum, exhaust pulses. You could do that with a MAP sensor. So if you guys have a known good one that's laying around and you have a pigtail for it, you can make that into a pressure tester. And the mass airflow, like I was saying, measures air volume and density based off of how much current it needs to maintain that certain temperature on that particular hot wire. So one thing you always want to remember when it comes to using a mass airflow sensor is, what is a normal reading? A lot of people always ask me, what's normal? What's normal? Well, first of all, you guys should always be looking at known good cars. And yes, I know some of you guys are going to say, I don't have the time for that, blah, 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 but you do. So car comes in, you guys are servicing it, and then you have to go for a test drive. Well, plug in your scanner, take it for a test drive, record all that data. Obviously, you're not going to come back and review it, but save it. And then when you have time, because you guys have time, go back and relook at the data. And this way you start picking up what is good, so this way when a bad car comes in, it's going to slap you in the face. However, if you don't have any of that, here's a good way of doing it. The old 1-to-1 ratio. For every 1 liter of air, for every 1 liter of engine size, you should get 1 liter of air. Okay, so if we got a 5.4 liter engine, we should be getting how much incoming air? Around 5.4, 5.5. Somewhere around 6 would be max, right? Okay, so that's a good way to remember it. This doesn't work though on Kia Hyundai. Just keep that in mind. So, because of that, the mass airflow sensor can actually cause some issues if the sensor is underestimating or overestimating the amount of incoming air. So one thing that we look at is total fuel trim. If you guys haven't been taught total trim, I'm going to give you guys a quick breakdown of it.
Trade executed.
So total fuel trim is when you add short-term and long-term fuel trim together, and that's actually how the PCM is determining how well the engine is actually running for air-fuel ratio. So if I add short-term and long-term fuel trim together, right, plus or minus 10% is okay. So if I add them together and I'm at plus 8, I'm okay. It is a little bit on the high side, but I'm okay. What we want to see optimal-wise is short-term and long-term fuel trim added together, giving us plus or minus 5%. That's what we want to see on a good vehicle. Always keep in mind that when you have a plus fuel trim, then that means that the vehicle is running lean because it's compensating for it. This is where a lot of technicians have trouble because they say, well, the vehicle's plus fuel trim. What do you mean it's lean? Well, that's a compensation. That is an effect of the problem, not the actual cause. And if you see a lean condition, if you see a negative fuel trim, that means that the vehicle is running rich, so the computer's trying to back off some of that fuel, so this way we can get the fuel back into stoichiometric. Okay, so remember that. If it's negative, it's running rich. If it's positive, it's running lean. Okay, so here's a good chart. This is something that I go over with my students. I also included alpha fuel trim for Nissans because sometimes it does get stupid confusing, and excuse my French. So if we have 0 fuel trim, we also have 100% alpha. If I have plus 5% fuel trim on a standard car, that would reflect as 105 on alpha. Or if I have negative 10% because I'm taking away 10% fuel because it's running rich, that would show a 90 alpha. Okay, so this way you guys can remember this in case you guys get a Nissan outside of ASC. If you get a Nissan that comes in for a diagnosis and you see that Nissan's at a 120 alpha fuel trim, you know it's actually running at 15% fuel trim. Okay, so keep that in mind. So mechanical ignition systems both passed. Now what do you do, right? So I like quick and easy tests. If you guys know me and you guys attend any of my classes, it's got to be quick and easy. And the reason being is if it's long, cumbersome, and hard, you're not going to do it. And you could sit here all day long, talk to me blue in the face that you're going to do it. You're not. Okay? And how do I know that? Case in point, compression. How many of you guys actually run a compression test when a car comes in with a misfire? Exactly. So that's the reason why I know that if it's a hard test, you're not going to do it. Okay? So I'd always start with sensor data, PIDs, before I move into anything else that's going to take more time to actually run. Okay, and what are some good PIDs to review? So let's take a look. So what are some good PIDs to review? One of them would be fuel trims, right? If I want to take a look at fuel trims, how are my trims doing? Are they positive? Are they negative? Are they within 10%? Are they within 5%? Are they at 30%? All that information is super important. Also, when the car is idling, why not look at mass airflow or MAP sensor, right? If my mass airflow, if the vehicle's a 5.4 and I'm showing 2.3 grams a second, that's a problem. That means that the vehicle is underestimating the amount of air, and that's going to give us a fault. What about engine coolant temp? Okay, so those are some of the PIDs you want to start getting the habit of actually looking at. The other thing that I always tell my students is never look at manufacturer-specific data when you're doing a drivability diagnosis. So what I mean by that is if you enter the VIN number to actually get to the vehicle information, you might be looking at a substituted value. So remember, manufacturers want the car to run and need the car to run, and also the system has the adaptive strategy. So your car is going to remember how sensor values work and all that. And if you don't believe me, grab a new car, start it, warm it up, and then walk out and unplug the engine coolant temp while looking at your scan tool. I guarantee you that more than likely about 90% of vehicles are going to show the same value with it unplugged. Why? Because your car remembered what the value should be, and it also looks at the intake air temperature, and then it knows what the temperature should be. So it's going to substitute it. This is why you guys need to be using generic data when you guys are trying to diagnose a drivability fault, because generic data cannot be substituted. Okay, so keep that in mind. All right, so here are some of the gases in combination that is going to indicate a rich condition. CO is going to go up, O2 is going to be minimal, CO2 is going to drop, HC is going to go up, and then NOx is going to go down. Okay, this is one good way of remembering it. If it's lean, you're going to have an increase, okay, of O2 depending on how severe the car is. CO is going to be really low. CO2 is going to be low. So if I have high O2, high CO, but low HCs, and that means the car's running lean. And then NOx obviously is going to go up, right up until I get to 16:1 air fuel ratio. After 16:1, it's going to start to go down, and the reason being is because at 16, anything above 16:1, the car is suffering from a lean misfire. Okay, so at that point, the unburned fuel is going to begin to cool down the combustion chamber, and it helps us reduce NOx. If I have a misfire, HC is going to increase, O2 is going to increase, CO2 is going to decrease, CO and NOx are going to decrease. Okay, so this is one way to remember it in case you think you have a misfire. All right, so the good old oxygen sensor. When it comes to an O2 sensor, a lot of people think, well, I got a P171, P0171, it must be the O2. No. That means the computer is letting you know that that sensor detected an anomaly. Now it's your responsibility to diagnose it. So the oxygen sensor circuit problems can cause some of the following issues. They can cause increase in injector pulse width. Think about it. If the O2 sensor is faulty or there's an exhaust leak and the O2 is detecting more oxygen, what does the computer think? Sees more oxygen, obviously it's lean, dump fuel. So it's going to increase injector pulse width and keep the injectors on longer, and that's going to make it burn more fuel. You might have a poor idle. The car is stumbling a bit, rough idle. That could be attributed to an O2 sensor. Hesitation on acceleration. So the moment that you accelerate, if the O2 sensor is responding too slowly, it's going to take a while for the computer to actually receive a signal from the O2, sensing the lean condition, for the computer to then compensate with more fuel. That can also lead to a surge on acceleration. High emissions. I've seen O2 sensors cause NOx failures, CO failures, and just because the O2 sensor is maybe 50 milliseconds slower than what it should be. Okay, and then lastly, it can also kill the cat. If the O2 sensor is bad, causes the computer to dump fuel, all that fuel is going to end up inside the converter. Then it's going to kill it, and then most people just swap the converter instead of actually checking what killed it in the first place. Okay, so one of the best ways to evaluate an O2 sensor is using a oscilloscope. Now, I know I'm going to get a lot of trash for this because you can see it from a scan tool. Well, do you guys realize that your scan tool has to knock on the door for the computer and say, hey, I need oxygen sensor data. Computer says, oh crap, looks for the data, shoots it back, your scan tool receives it, converts it, then puts it on an actual graph. That data is old, okay? And I could prove this to you because we've done this test in classes. But if you want to be the tech who uses that scan tool data, go for it, okay? The problem is if you are going to be using that, you need to isolate the PIDs to 1 or 2 PIDs max. So this way you can get the fastest refresh rate that you possibly can. Okay. Also, if you guys are using the new fancy wireless stuff, it's even slower. Okay. So keep that in mind. So what you want to look for is you want to look for good amplitude. Amplitude always is what? Voltage, right? And we want to look at good frequency, or our hertz. So anytime we're looking at a normal zirconia O2 sensor, you want to see it go from 100 to 800 millivolts, right? With 450 millivolts being the center point, and you want to see it switch from lean to rich at least 1 to 3 times per second, okay? So one of the ways that you can do it is raise the RPM to about 2000 RPM and watch it on your scanner. And your O2 sensor should switch about 1 to 3 times per second, okay? And that's going to indicate that the O2 sensor is okay. Problem is most states, including California, if this is an emission repair and you don't scope it, you can get into some serious trouble. Okay, so make sure that if you guys are in California or any state that has these types of regulations, New York in case, you guys should be using a DSO or a lap scope to actually check an O2 sensor to condemn it. Okay, so right here what I'm doing is this is a propane enrichment test. So here what I did is I added propane. As you guys can see, the vehicle is running rich. I turn the propane off, and then the vehicle begins to come back down to a lean condition. Once I get to the furthest lean condition, I snap the throttle. Okay, when I snap the throttle, we should get an instant rich condition, and then I'll go ahead and pause my screen. Then I'm going to put 2 cursors, one at the lowest point and one at the highest point, and I'm going to read the amount of time it took for that O2 sensor to switch from lean to rich. That reading should be less than 100 milliseconds. If it's not, you got a problem. Okay. I share this story a lot. I had a Cadillac that came in once, had brand new O2 sensors, diverter valves. It had an air injection code. So most people were telling me, hey, well, it's got to be the pump. I said, well, why? Oh, it has new everything, new this, new that. It's like, okay, well, why not test it? We already did. All right, so I had him drop it off, and I tested the vehicle. So when first thing in the morning I got there, started the car up, it ran the air injection. I heard the pump come on, but it still set a code. So me kind of doing some research, I found out the O2 sensors were the line of defense for the air injection. The computer looks at the O2 sensors to make sure the pump actually came on. So I ran this test. Brand new Bosch O2s failed. They were about 250 milliseconds from lean to rich. I said, this can't be. I reran the test, same thing. So I called the customer. I said, hey, I need you to bring me 2 AC Delco O2 sensors. It has brand new ones. I don't care. I need 2 AC Delco sensors. Sensors got there. I swapped them out, reset it. I said, look, let the car run its test, and we'll test it in the morning. So I got there in the morning. Some of you guys have probably been in this situation. I got there with butterflies in my stomach, kind of dreading it. Like, hopefully this takes care of the problem, right? Because that was the only thing that I found wrong. And being the shop foreman at the time, and then being the only shop in that complex that actually knew what they were doing, I had a lot of weight on my shoulders. So I got the car started. I heard the pump come on, ran the test, and about a minute into it, idle came back down to normal. I said, all right, cool. Fingers crossed, shut the car off, put the scanner on. No pending codes and no codes. And guess what monitor set? Air injection. So it was the 202s that were actually too slow. So by the time they actually detected the pump airflow, the computer said, now I don't like this, set a code. Okay, so this is why it's important to understand how does the system work and how can I dynamically test this vehicle. Okay, so again, like I was saying, when it comes to mass airflow, always remember that as airflow increases, current increases. Airflow decreases, current decreases. So air equals amps anytime we're talking about a hot wire mass airflow sensor. And always remember, for quick reference, the 1-to-1. For every 1 liter of engine size, you're going to get 1 liter of air. Okay. So this is a quick mass airflow test that we ran using a scope. One thing that you guys want to pay attention to when you guys run this test, this first inrush should pass about 3 volts. Okay, 3.5 would be good, but it should pass about 3. Then after that, a lot of people ask me, why does it come down? Well, think about it. When you snap the throttle, right, air and fuel is going to rush in. But what's going to rush in faster is air. But fuel's going to take longer because it's denser, it's heavier. So it's going to take longer to actually move. So when you snap the throttle, you're going to have a huge inrush of air until the manifold is full of air. So then what happens is engine speed or airflow speed slows down. Then as the engine catches up, then it comes back up to normal. Okay, so this is what you would want to be seeing if you guys were dealing with a normal hot wire type mass airflow. If you guys have a mass airflow that is a digital, such as GM, you can actually use a Pico lab scope, and it will give you this type of waveform if you set it up to frequency. And then it's going to give you this waveform when you do a snap. This is one of the reasons why I use my Pico when it comes to mass airflow testing, especially if I know it's a digital type mass airflow. Continuing with fuel testing, right? I always ask this: would you guys prefer to check fuel pressure or fuel volume? Okay. If you guys said fuel pressure, I'll tell you why I don't recommend it in a bit. I always check for fuel volume. And the reason why is because fuel volume is going to tell me, do I have enough volume of fuel to run this engine? Okay. When we're talking about a fuel pressure regulator, or fuel pressure, I'm going to use this lid as an example. So this lid is actually acting as my fuel pressure gauge. My gauge is sitting here, and I have a hose connected to my Schrader valve. When fuel comes up to my gauge, right, it's going to stay there, and then it stays inside of the fuel line. So it's only going to increase in pressure, never decrease. So if I get a moment where my fuel pump stops delivering fuel, I'm never going to see it on my gauge, right? So this is why I never recommend checking fuel pressure. I always recommend checking fuel volume. I've had vehicles that had perfect fuel pressure, but it had no fuel volume. So if I don't have volume, then there's not going to be enough fuel to actually sustain a running engine. So on a non-modulated fuel pump, you should get 1 to 3 pints for every 30 seconds of cranking. Okay, so release the fuel pressure gauge. Here's the easiest way to do it. Around the shop, you guys somewhere have a 16-ounce water bottle, right? You bought it at Costco, Sam's Club, whatever. 16 ounces. You grab that sucker and then empty it out, and you're not going to reuse that fuel. You put on your fuel gauge, and your fuel gauge has a bleed valve. Get that bleed valve, put the hose in the water bottle, hold it open, and crank it for 10 seconds. If I crank it for 10 seconds, what should I have? Okay, you should fill up that water bottle within 10 seconds. If you don't, your fuel pump's weak, and it's probably going to need a replacement. Then you can follow that up with pulling the fuse or the relay for the fuel pump, putting an amp clamp, and watching it on your scope. Check to see how your armature is doing on it. What if the armature is bad on it and you need to replace the fuel pump? Okay, now you have two definitive tests that prove that fuel pump is bad, right? I always like to prove it more than one way. Why? Because what if I tested it wrong the first time? Okay, so before you condemn something, make sure that you run multiple tests to make sure you're getting the same conclusion. Okay, with exhaust restrictions, like I was mentioning before, there's a couple different ways you guys can actually do it. One is you can use a vacuum gauge, snap the throttle and make sure vacuum drops to 0 and then comes back up. That's going to tell you that you have a good no exhaust restriction. The other way would be to do a in-cylinder pressure transducer test. So if you guys aren't aware how this is set up, this centerpiece right here, this is the exhaust plateau. So notice that exhaust is measuring 0 psi. Well, that makes sense, right? Because exhaust is not vacuum and it's normal atmospheric pressure. So it should be about 0 psi. This right here is letting me know that I have no exhaust restriction. But what if the moment that I'm looking at this trace, I'm seeing from this point where my mouse is at going all the way up to here and then coming down, that's telling me that gradually pressure is increasing. The only way pressure can increase is if I'm restricting the exhaust. So this is one way for you guys to do it. And this is a good method to use when you have two banks and you want to figure out which bank is the one that's actually restricted. The other way of doing it is if the vehicle has a MAP sensor, MAP, you're going to raise the RPM and hold it about 2,500 RPM. If your MAP sensor continuously shows atmospheric voltage or pressure, what does that mean? That means that the manifold, the intake manifold pressure is equal to atmospheric pressure, which there's no way because vacuum is what? Vacuum is intake manifold pressure minus atmospheric, right? So it's less than. If they're equal, that means that you have an exhaust restriction. So that's another way that you guys can actually take a look at that. All right, so continuing, we're going to go at emission system, diag, and repair. So one of the first systems we have is what? Our PCV valve. So the PCV valve's responsibility is to allow the blow-by gases from the crankcase to be recycled back into the intake where we burn them off. Okay. One thing that we're seeing a lot now, Nissan's having a pretty big problem with their PCV valves. They're giving a lot of lean codes. Guys are throwing air fuel ratios, mass airflow codes. I've seen mass airflow codes for these as well. Okay, so be careful with that. Make sure you guys are properly checking them. So one of the ways that you can actually check a PCV valve is by pulling it off, right? You pull it off, and if it's removable, because not all of them are now, so you can remove it and then see if your RPM changes, right? The other way is take the valve off and shake it. Make sure that the plunger inside is actually moving. And if it is, it's probably in good condition. Or remove it and put your finger underneath it and see if you're getting vacuum coming out of it. Okay. If you guys run into some of the Volkswagens that have a molded PCV valve on the valve cover, we've seen with those is customers will come in with a complaint of a whistle, right? And it sounds like a belt squeak, but it's actually the PCV system is failed. So now you got vacuum in the whole crankcase. One of the ways you could do this is pull the dipstick, and if the squeal goes away, it's a bad PCV. The other way we've done it, and we learned this from ATG, is using propane around the bell housing. If you run propane around the bell housing and RPM increases, then that propane is actually being drawn in through the rear main seal, and that's letting you know that the PCV system is actually shot. Okay, so that's one way you can actually test as well. So here's some of the common codes that you might see for defective PCV system. P101 and a 505, idle air control and a mass airflow. So most shops, if they get a 101, what's going in the car? A mass airflow. Once that doesn't fix it, then it's probably O2s. Once that doesn't fix it, then it's maybe a computer. If that doesn't fix it, send it to somebody who's actually going to check it. That's usually how it works, which sucks because it makes the good guys look bad. Okay, here we're looking at a non-enhanced evap system. Non-enhanced evap systems usually run between 96 to 99. And this system doesn't check for leaks. It only checks for flow. So here we have a flow switch, which I'm circling right here in number 8. This switch is closed. So in its normal state, the switch is actually closed. And then right here in front of it, it's a purge valve. Look where it's connected to, vacuum. So the moment this purge valve is energized, vacuum now goes through the purge valve, opens this switch, and then pulls everything out of the actual canister. When this switch opens, that's how the computer knows we have flow. Did it actually reach the engine? We don't know. Right? System's looking at for flow. Then it's going to look at the O2 sensors to see if they went rich. If they did, the computer knows there was successful flow and it actually reached the combustion chamber. But if there was any leaks, nothing, right? This is why on some of the older vehicles during smog inspections or emission inspections, we actually check and test the evap system. From there, we went to an enhanced evap system. This is a vacuum decay evap system. Okay, so this system right here uses a vent solenoid, a purge solenoid, a fuel tank pressure sensor, right, to actually test itself. An enhanced evap system will test for leaks and it will actually test for flow as well. So the way we break this down is to keep it really simple. Is the front door at your home, hopefully in theory, is always closed and locked. A purge solenoid is the same thing. Okay, we usually keep it closed until we need to either draw fuel vapors out of the canister or allow vacuum into the system to check it for leaks. So the purge solenoid is going to be your front door, usually closed, and will only be open to allow vacuum into the actual system. Your back door, okay, is a vent solenoid. The back door on the vent solenoid is always open, okay, and it's open to allow fresh air in to push vapors through the canister and back into the purge, into the engine to burn it off. Okay, so the vent solenoid, this is the one that gives us a lot of problems. Why? Because as this is always open, there could be, I've seen spiders, spider webs, rocks, mud, all in here. Okay, so when the computer commands it closed, it can't close because it's either damaged, restricted, something's holding it open, and then that's going to give you a large evap leak. Okay, so case in point, always take a look at these vent solenoids as well. And the fuel tank pressure sensor is just a fancy name for a MAP sensor, MAP. This sensor sits on top of the fuel pump or on the tank, and it's going to be measuring the vacuum applied to the tank. So when the vehicle is testing itself for leaks, it's going to open the purge valve, close the vent solenoid, allow vacuum into the system, and it's going to fill the tank with vacuum. Once it's full of vacuum, it shuts the purge solenoid off, keeps the vent solenoid off, seals the system, and then it's going to monitor the fuel tank pressure. If fuel tank pressure remains at a constant level, then it knows there's no leaks. If it begins to drop off, it's going to measure how long it drops off for, and then it's going to know if it's a small, very small, medium, or large leak. Okay, then it's going to set a code for it. I've also seen these fuel tank pressure sensors actually create false codes. One way to test for a fuel tank pressure sensor is, this is how hard this test is. Plug in your scanner, look at the FTP, go and take the fuel cap off. If I take the cap off and pressure changes, sensor probably works. Okay, so that's one of the easier ways to actually do it without actually dropping the fuel tank. Okay, the next emission component we're talking about is exhaust gas recirculation valve, or EGR. So the EGR's responsibility is to help us reduce NOx. Anytime you guys are diagnosing a NOx problem, always think about, does this car have an EGR? And if it does the EGR work? Because the EGR's responsibility is to help us lower NOx. Okay. So the one you guys are seeing right here on the left-hand side is a back pressure EGR. This is a positive back pressure valve. So this valve right here actually needs exhaust gas to actually open the valve. So this one doesn't use vacuum like our negative back pressure EGRs. So this one, the way we check them is mirroring a flashlight, and we use one of the inspection holes right here to actually see if the diaphragm's lifting. Usually you have to power brake the vehicle to create enough back pressure for it to lift the EGR up. Or what I do is I'll shove a camera in there, borescope, and then watch my camera screen, power brake it, and watch that valve lift. If it lifts, then I know the valve's lifting, and it's not going to be the actual valve. If it's a vacuum operated valve, make sure that the vacuum to the actual tip is working. As vacuum is applied, it's going to lift the diaphragm, and then that's going to allow exhaust gases into the intake. Same thing on the positive back pressure EGR. The reason why we're putting exhaust gases into the intake is because oxygen in the exhaust has already been used up. Because there's no oxygen, it's an inert gas now. That inert gas is going to cool down the combustion chamber, and that's going to help us reduce NOx. Anytime we go above 2,500 degrees Fahrenheit in the combustion chamber, we lose control of NOx, and then NOx goes through the roof. Okay, so here's an air injection system that I was talking about earlier. Okay, this is an electronic one. Here's our electronic pump. Okay, here's our secondary valve, and here's our electronic switch. This pump is going to be commanded by the PCM to a relay. Relay turns on the pump. Pump then goes to this valve here, this check valve. this vacuum solenoid applies vacuum to the check valve, and then that allows air downstream into the exhaust, where then it's going to help us warm up the cat, begin to oxidize and reduce HC and CO on cold startup. If this was an old belt driven pump, okay, once the cat was good, then the diverter valve would close and then open this to atmosphere, because this pump was belt driven, so it was always producing oxygen. So that diverter valve will then push it out into the air and you were golden. With the new electronic ones, they just turn them off and then you're ready to roll. Alright, so let's talk about some computerized engine systems. So one of the sensors we want to look at is TPS. This is an input, right? So this is a potentiometer. This potentiometer is going to convert movement into a variable voltage, okay? So like any 3-wire sensor, what are the 3 wires? You should have said power, ground, and signal return. Or reference, right? VREF, ground, and signal return, okay? So depending on how much we move the throttle is going to be how we vary the voltage. One thing you guys want to remember when it comes to a TPS, you usually want to see close throttle at idle between 0.5 volt to 0.7 volt. Outside of that might indicate a problem, or it might be a drive-by-wire system where the throttle position sensor is actually connected to the throttle plate itself. Here what we're looking at is we're looking at a lap scope screen of a bad throttle position sensor. So as I begin to accelerate, voltage goes up, but then you guys notice this huge dropout here. Whenever I have a dropout like this, the computer can't tell the difference between a bad sensor and you letting go of the throttle. Because of that, when the computer sees a dropout like this, what it does is it's going to back off the fuel, so then the customer is going to complain of, hey, I'm on a light and I gun it, and it takes off and then just does this, and then it takes back up. That right there is letting you know that for some reason the computer backed off fuel. And this is a very common problem, and it won't set a code. I had a customer that brought me a Mitsubishi for an EGR code that wouldn't, EGR monitor that wouldn't set. They had replaced EGR, O2 sensors. They were about to replace the computer before I got it. This was during COVID, so I actually diagnosed it here in my house. When the car got dropped off, I told him, leave it there. I'll check it right now. Came inside, grabbed my scan tool, went outside, plugged it in. Key on engine off. The first thing I noticed was my throttle position sensor was over 1 volt. That was a big problem. So came back inside, grabbed me a stubby Phillips head screwdriver, unscrewed it, backed it off. Best I could get it was like 700 millivolts. Tightened it down, cleared the light, and I left my house. I think I got about a 1/2 mile from home before the monitor set. Came back home, checked it, no pending codes, everything was golden. Called the customer, and he's like, there's no way. I was like, yeah, it's done, man. So I charged him a diag fee. Why? Because it was my time, my knowledge to actually diagnose that. All it was a misadjusted input. So this is why inputs and input verification is very important. A potentiometer just isn't for throttle actuation. Right here, this is a EVP or EGR valve position sensor from a Ford. So if you guys have been around for a while like I have, the old Fords used to have a linear position sensor that sat on top of the valve. This is how the computer would know if the valve actually opened. Okay, so it works the same way. Power, ground, signal, return. Depending on the position of the sensor is going to be the voltage going back to the computer. I had a Chevy Venture once that I worked on. A shop brought it to us because they couldn't get the EGR code to go away. New EGR was installed. The car was in the same condition. First thing I did, key on engine off, plugged in my scanner. Position, 0. Cool. Started the car up. I said, wait a minute. Position actually showed like 12% open. I was like, that's not normal. So then I said, well, the only way that position sensor could be open is if electrically something's commanding the EGR on. So I turned the car off, opened the hood, and the first thing I noticed was that the connector for the EGR was super stretched. And the EGR kind of looked weird to me. Well, what ended up happening is 2 shops in a row installed the EGR on backwards. So they put the position sensor, which was this side, on the exhaust positive side. So when the exhaust pressure built, it actually lifted the EGR open, and that would go into the intake, causing a rough idle and giving me an EGR code. All it was improper installation due to improper verification and actually checking it more than anything. What tech could have done is pull the EGR off, started the car. Yeah, it was going to run like crap, but then you could verify which one was the exhaust port, which one was intake, and go from there. But no, they just kept putting it on in the same position backwards. And this is why it goes back to always check the basics. So here we have an engine coolant temperature. This is an NTC type coolant temp. Okay, so we have a 5-volt reference feed to the sensor. Depending on the voltage drop inside of the thermistor, is going to go back up, and then this signal return over here to the side is how the computer is going to know what the voltage drop is of the actual thermistor. Depending on the voltage drop is how the computer knows what the actual temperature is of that particular engine coolant temp or intake air temp, cabin temp, or whatever that sensor is actually detecting. So here I give you guys a quick graph. Notice how as resistance begins to drop, right, that's telling you that the temperature is actually getting hotter. So that's a negative temperature coefficient. Okay, as the vehicle gets hotter, voltage actually goes down. Okay, and if you have a PTC, it's going to be the opposite. As the vehicle gets hotter, voltage goes up. Okay, so on most cars, it's an NTC type. As the vehicle gets hotter, voltage drops. Okay, so like you guys could see here, cold engine, we're almost at 5 volts. Normal operating temperature, we're at 500 millivolts, somewhere around there. Okay, so always keep that in mind. So here's our fuel injectors, okay, and here's the armature that's going to lift the pintle. Once this is magnetized, then it's going to allow the injector to open and then allow fuel to come out of it. If you guys don't remember or have never used a lap scope on a fuel injector, here's a fuel injector trace. This is source voltage A to B. At B, the computer turns on the driver and pulls it to ground. So as it pulls it to ground, from B to C, this is the on time of the injector. This is how long that fuel injector was actually on and spraying fuel. Then when you turn off the fuel injector, you're going to get a voltage spike. This is absolutely normal. You want to see this voltage spike go above 35 volts. If it didn't, then that's indicating to you that that injector is actually weak. The armature in that injector is weak, and that injector needs to be tested a little bit further. Then after that, around here, you usually see a small nipple, and that little nipple is indicating that the fuel injector actually came back to its seat. Pintle seated, okay? And then E, again, is going back to its normal reference voltage. And then here we're looking at an idle air control valve. Some vehicles now don't use this because it's integrated to the throttle plate. But if you do have to diagnose a car that has an idle air control valve, always keep this in mind. If the vehicle is idling, but your idle air control valve shows 0 counts or 0%, that means that the valve is fully closed. So how is it that the car is actually on? If this valve's responsibility is to maintain small amount of air to keep the engine running, and this is fully closed, how is the engine running? If you guys said vacuum leak, you're spot on. Okay, I got to diagnose, my first time I ever ran into this was on a Saturn. Came from another shop, customer's complaint was erratic idle. And first thing I noticed was idle air control was 0. So I said, how is this at 0 and I'm at about 1500 RPM? Pulled out the propane enrichment tool and I found a vacuum leak on the intake manifold gasket. Called the customer, she didn't believe me. And obviously it's kind of obvious. Well, shop A already, took a lot of money from her and the problem was still there. So she was kind of reluctant. I told her, hey, look, these are the tests I ran. If you want to come down, I'll show them to you. Finally she agreed to do the gasket. We did the gasket, took care of the problem, and she was a lifetime customer. Once I left the shop, she was actually still a customer of the shop. So this is important to make sure that you guys understand how does the system work and what am I expecting to see on this particular system. Here's a diagram from GM. Okay, this doesn't apply to all vehicles. Keep this in mind. And I showed this to my students not too long ago on a Toyota that we have here as a lab car. Our Toyota has a map sensor, right? And at idle, it wasn't showing the vacuum as we see it here on this GM. Okay, so we had to look up the spec from Toyota, and the spec is different. So this is just a reference, but this is not to anything outside of GM. This is GM only. Okay. So whether you're dealing with a map sensor, fuel tank pressure sensor, or fuel rail pressure sensor, it's the same thing. Okay, it's a pressure sensor, absolute pressure sensor. So voltage is going to increase, right, as pressure increases, right? So the lower the voltage means you have vacuum. So inside of the map sensor, when the car's at idle, it should be about 1 volt. Why? Because I got vacuum inside of the engine. Okay, so keep that in mind. All right.